Now here we have an impossible triangle. We look first at this corner, and it's telling us that there is a wooden triangle which is facing in that direction. Now if we go up here, we see this corner, and we're told by our eyes that there's a triangle facing in that direction, and now we're told there's a triangle facing in a third direction. Those three angles don't match up together. They can't mix together, and yet the brain sees it, constructs in the brain a model of an impossible figure, an impossible triangle. And I imagine all of you can see that. Now we're going to shatter the illusion rudely. What's happened? Out again. The triangle's reformed. In again. Out again. Thank you very much. Would you like to bring in the object now, and we can see what it really is? Thank you. I'm sorry, I didn't get your name. Sarah. Right. Now, you can stay there for a moment, Sarah. You see, it's nothing special about it at all. It's just 3 bits of wood glued in opposite directions like that. I'm going to move it round and try to recreate the illusion. I haven't done it terribly well, but there it is. And now I think if I put my face in, you can again see it happening like that. Okay, thank you very much, Sarah. Now here's one of the great classic illusions, which is the best one I have to make the point I'm trying to make. This is called the Necker cube. And it's just a picture of a cube drawn on paper. If you look at it, I think you'll see it doing a rather strange thing. It'll be alternating. The side that seems to be nearer to you will change. Sometimes it'll be one side, sometimes it'll be another. What's going on here? Well, the two-dimensional pattern of ink on the paper is equally compatible with 2 alternative 3-dimensional cubes. So the brain doesn't know which of its 3-dimensional cubes to use. It's got 2 potential models of 3-dimensional cubes in there waiting to be used. And it doesn't know which one to use because both of them are equally compatible with the 2-dimensional pattern of ink on the paper. So what does it do? It could plump for one or other of them, but it doesn't do that. What it does is alternate. And so you sometimes see one and you sometimes see the other. Now this is a more elaborate version of the same thing, because this is a real cube, as you can see, made of metal, and it's rotating. But once again, if you get the lighting right, it is sufficiently, perhaps it's best if you look at it on the screen here, the 2-dimensional pattern that's moving around your retina is equally compatible with 2 different 3-dimensional cubes. And so if you look at it and perhaps blink, look away and come back again, you may see it change direction. And what's happening, as I say, is that the brain doesn't know which of 2 models to use, and so it chooses them alternately. But we don't have to go to the lengths of setting up illusions with apparatus to satisfy ourselves that the brain does set up a virtual reality model. Here's something we can all do without any apparatus at all, again including people at home. So this is something you do to yourself. You won't see anything on the television screen if you're at home. You'll just do it to yourself. Just very gently with your finger, move your own eyeball. Just poke it up where I'm doing it. See where I'm doing it? And I think what you'll see is that the world moves as you do it, doesn't it? It's like a little minor earthquake when you do that. Well, of course, that's exactly what you'd expect, isn't it? Because the image on your retina is being moved. The eyeball is being moved. And so the apparent position of the object you're looking at is moving. So you see it as movement. What's so strange about that? Nothing strange about that. That's just what you'd expect. But now let's think a bit further. Because doesn't something very similar happen whenever you roll your eyes about? If I roll my eyes like, do it now, just roll your eyes, move your head about, roll your eyes. The image on your retina is going crazy. Much worse, in fact, than when you simply poke your eyeball with your finger. The image on the retina is moving, but what are you actually seeing? You're not seeing the world moving like an earthquake. When you roll your eyes about, the world appears to be as steady as a rock. So on the one hand, when you poke your eye, the world appears to move as though there's an earthquake. On the other hand, when you voluntarily wiggle your eyes about like that, although the same thing's happening on the retina, what you see is a perfectly steady world. Why is that? What's the difference between those two cases? Well, it's this. There might really be an earthquake going on, and it's important for the brain to know. On the other hand, it's also important that the brain should not constantly think there's an earthquake whenever you move your eyes about. So what the brain does is whenever it sends an order to the eye muscles to move the eye, to roll the eye, which it often does, it sends a copy of that order to the virtual reality software that's engaged, that's busy setting up the model of the world. And the virtual reality software is told, okay, the eye's about to move, expect the world to move. And so the virtual reality software does not see an earthquake because it's been told to expect it. The model in the head is precisely compensating for the anticipated movement. But when you poke your eye, no copy of any order is ever received. And so the world really does appear to move as if there was an earthquake. And indeed, there might be an earthquake, and it would be important for the brain to know that and not just to immediately discount it. Now, a very clever experiment on this was once done by a German scientist who put his own eye muscles out of action with an anesthetic. Now, I was going to call for a volunteer for this experiment. We have a volunteer, but I think, unfortunately, there isn't any time, so we'll have to... I'll just have to tell you what happened. What this German did was he anesthetized his own eye muscles. Now I think what would happen. Whenever he told his eyes to move, they didn't. Nothing happened. They stayed absolutely stock still. And the image on the retina stayed absolutely stock still as well. But the copy of the order had gone out to the virtual reality software in the brain. And the virtual reality program was told to expect a movement. So when no movement came, it interpreted it as if it was an earthquake. So whenever this German told his eyes to move, whenever he gave out the order for his eye muscles to pull the eyes around, the eyeball stayed absolutely still, the image on the retina stayed absolutely still, but the model in the brain moved, and he saw an earthquake. So that's my evidence that the brain is setting up a model of the world. We're seeing virtual reality. I now want to switch temporally from that topic and talk about the evolution, the growing up of the human brain itself. By evolutionary standards, the brain seems to have grown up very, very fast indeed. One authority has said that the evolution of the human brain over the last million years or so is perhaps the fastest advance recorded for any complex organ in the entire history of life. And compared with the skulls of other apes like chimpanzees, our skull is indeed very big. It seems to have blown up like a balloon. And here's an animation of that. This is the head of Australopithecus, which is one of our ancestors. And now you can see the evolution gradually happening before your eyes. It's becoming a Homo erectus. It's an early Homo sapiens. It's changing now to becoming a modern Homo sapiens like us. Look how the skull is ballooning out. The head is ballooning out as evolution goes by. We've compressed about 3 million years of evolution into that animation. Now here's the same thing from the side view of the skulls. Here's Australopithecus again. Look, quite a low head. Now it's going bigger, the jaw's coming in, evolution's going by, millions of years going by, and the skull is blowing up like a balloon, blowing up, blowing up. There it is. There's a modern skull. There's a modern human skull, chock full of brains.